Very good. Before we start, is there any question? Any question, any suggestion, small talk, long talk, big talk, anything related to our course? We've been here for 3 consecutive weeks now, and I want to know your opinion, your question. If there is still anything is not clear, please let me know. Any question 10, any question 9, any question 8, any question 7, any question 6, any question 5, any question 4, any question 3, any question 2, any question 1. Really, people? No question? Okay, wonderful. Let's start. I want to show you the quiz that you had. Of course, it had different variations, if I can find it. Yeah, very good. And by the way, for those of you who don't know where to find the video, the captured video of previous weeks, this is the place. So as soon as you join to join session, and then you launch Big Blue button, it gives you the link to all previous lectures, except for lecture 2 that I had problem recording locally. Lecture 1 and lecture 3, week 1 and week 3, also I recorded them locally and I uploaded to YouTube every time I'm sharing the link in Microsoft. Also one important thing, today we will have one presentation which is by Naveen. Naveen sent me a video of his presentation, and we will see that at the end of today's session. So today we will have quiz, review of quiz of previous week. Then we will have lecture discussions. We will see the activity of this week, and then the presentation. After a break, we will the ending part of today's session will be presentation of students. The only student presenting this week is Navi. Okay, because I didn't hear about presentation from the other student, Brightly, I believe. So I didn't from. So we will not have any presentation, just from Navi. Okay, great. So let's go review quiz questions. Quiz questions. This time I'm gonna open my grade center test. I'm just gonna randomly select. Guys, this is how I see these submissions here. So some people said they cannot. Oh, by the way, I shouldn't show this, right? So let's close this and let's do it the other way. Courses, quizzes. Let's directly go to quizzes and see quiz 3. Quiz 3. I want to attempt this quiz. Let's see what we have. Okay, the first one is I know you probably see some variations to these. This is not exactly what you've seen because we have some kind of variations in these questions, but more or less this was the same thing. So I guess people really did well on this part. I think for they knew the meaning of computers. Computers are well basically uh, electronic devices for storing and processing data. So you can do storing and processing data on computers. Computer programming is a process that leads from the formulation of a problem to an executable solution. So what you do in computer programming is basically you have a problem. You first look at that problem uh, from the perspective of, now how can I solve this problem? In what steps? Step 1, step 2, step 3, step n. These are the steps that I'm going to tackle this problem and solve this problem. Then for each of those steps, or for the whole program, like in all the steps, you start writing your code. And for that you have plenty of options, programming languages available, that each is useful and efficient and easy to use in some ways. That is the topic of this session that we will discuss. Software versioning. This, I believe, is talking about the software development lifecycle uh, that we talked about, SDLC. So in that topic, we said that all the softwares are developing. So you first give out the version that you think is the best. You have tested on your local computer or server or whatever, but the only test that has been done on this piece of software is you, or probably your colleagues, but not it. This software, typically called beta version, is the software that has been tested with a few people, and if they couldn't catch a bug, or they, like, everything was fine, or they could find a few bugs and did some fixes, then that will be available to a larger group of people. So software versioning comes from here. Also, so all the softwares, as you have seen, get updated unless they are outdated, and the company, or the if it is a closed, basically a commercial license, the company either doesn't support that version or that piece of software anymore, or if it is open source. Uh, this happens less for open source softwares. The team that is developing this, uh, a team of developers that are working voluntarily on a project, they stop supporting, or they stop making updates for a version of a software or for the software. So basically, in summary, software versioning uh, is the assigning is for the purpose of sharing resources, is for assigning names, version numbers to software development. Yeah, this one, assigning unique names or version numbers to states of computer software development. Then a computer network is, so we know that the computer network is a collection of computers connected by any means. It can be connected through the internet. It can be through a local net, intranet, whatever. So those are the uh, for those who know, giving someone processed at least, maybe developed in a collaborative public manner, electronic device. Which one is this, guys? A computer network is for the purpose of sharing resources. Yes, it is as asking about the purpose of computer network. So what do we benefit from connecting computers is that we share resources, right? So for example, imagine cloud is these days is one of those concepts that people like. Why? Because when you have the possibility of doing all your computation on a cloud, you end up having less expensive, less complicated user devices. So your laptop can be just a simple laptop. You don't need that much computation power, right? So this reduces your cost. That's why people like it. And with connecting those, by sharing those resources, we end up having more powerful computers. So imagine your program being run on a computer that has uh, 64 CPUs running at the same time, or just having your computer just one CPU with probably two cores or four cores or eight cores. So the purpose of computer network is to share resources, and that's what we benefit from that. And by resources, we mean the hardware, right? Hardware or software. So the things that allow us run our programs and do computation, stuff like that. Open source software, we know open source software may be developed in a collaborative public manner, of course. So for most of the open source softwares are like this. So there is no single organization or a company that develops this. It's a group of people. Usually, it typically starts like this. Somebody volunteers for something very interesting, and then other people join. And then that's how these open source softwares uh, get bigger and bigger, and that's the development process for them. Authorization is giving someone permission to do or access something, right? We had authorization and authentication. Authentication was a machine authenticating a user. If I am who I should be, if it is somebody else trying to access my account or my sensitive information, or if it is me. So that part is authentication, and for authorization is comes typically after authentication. So you authenticate the user when the user is okay. Now you're you. Then okay, go ahead. I give you authorization to access uh, different levels of authorization. Of course, we have. You can access this. You cannot access that one, and so on and so forth. There are 10 types of people. I typically read it 10. You do so, but we know this was a joke about binary. So we will see this different presentation of numbers in different bases, typically base 2, base 4, base 8, and base 16. Base 2 is called binary. Base 8 is called octal. Base 16 is called base 16 is called hexadecimal, and base 10 is called decimal. So 10 is the most familiar. This is how we do our calculations, what we have learned in primary school, and this is what we know as humans. Base 2 is what computer understands. So we need to know base 2 to be able to, sometimes it's necessary to be able to even debug your code. Uh, very good. Any question, any discussion so far? Please just unmute yourself and ask a question if there is any. Uh, this one, many people got it wrong, really wrong. I don't know why, but we had it in the slides and we discussed this. So what comes last here from level 1 to 4? What comes last? What is the very fundamental physical layer of what we have is the hardware, right? Hardware is the machine, is the thing that we have to be able to even think about operating system application and things like that. So what comes here is hardware. On top of the hardware is the operating system. So we said that, imagine you go to a restaurant, okay? So that restaurant, that physical area of the restaurant is the hardware, right? The kitchen, ingredients, everything that you see there, chairs, table, everything you see there is the hardware. Then operating system comes on top of that hardware to make people be able to interact with that hardware. You cannot go to a restaurant and make your own pizza, right? You have to ask the people working there to prepare your pizza and give it to you. So the people that work there, basically the staff working in that um, physical area, is similar to what an operating system does. It basically links you to that physical area. This is you, and this is the physical area. What links you to that physical area is the operating system. Why? It's clear because I don't know how to make my own pizza in a restaurant. I don't know how to turn on the oven. I don't know where is what, where to find what, things like that. I really don't know anything about that kitchen that is making my pizza, right? So I have to communicate with an interface, which is the staff working there, to be able to get what I need. Exactly the same thing applies to hardware, operating system, and applications. In the early days, it wasn't like that. So everybody coded directly for the CPU that they had. There was no operating system, uh, and they saw that okay, now everybody that wants a slice of pizza need to go read manuals, see how this oven works, what ingredients they need. They need to go get the ingredients, and just making or eating a slice of pizza became so difficult that people started thinking, okay, now we need an interface that knows how this thing works and at the same time understands what the user wants. And that was the time that operating systems were born. Operating systems come on top of the hardware. They know how the hardware works. They know exactly what is where. They know exactly all these registers. Like if you go and read manuals of some of these hardwares, you will see they in 2000 to thousands of pages they describe how you should do a single task, and it was impossible for everybody to know that amount of detail about hardware. So operating systems started doing the job of, okay, now they know how to communicate with the specific hardware, and they serve you with whatever you want. So on top of the operating system comes the sorry, on top of the hardware. Hardware is the lowest layer. Comes operating system. On top of the operating system comes the application. Now, when you have the operating system that knows how to interact with your hardware, a single operating system is not enough to fulfill all users' demands. Somebody wants to type something, somebody wants to calculate something, somebody wants to watch a movie, somebody wants to chat with somebody. So for all these capabilities, for every single one of these capabilities and needs that the user wants, you need a specific application. That's where software development comes in, and that's where most of you will probably be working in the future. Even though I saw some people are interested in the hardwares, like myself, those people will belong to a very interesting and growing field of job opportunities, which is embedded system, and we will somehow we'll talk about it today. And on top of so it is hardware, operating system, application, and then the user, right? So this is the four levels of uh, things that we have in ICT world. Very good. what does GUI stand for? So GUI stands for Graphical User Interface. Uh, some interface that is graphical. You can click on something, you can select something, and things like that. Again, we will talk about it today in a couple of slides. Some people had this another acronyms, uh, maybe command line interface instead of graphical user interface. So it was command line interface, CLI, which is the type of interface. Basically, you have two major type of interfaces to interface with the operating system. One is this graphical user interface. Windows is the the most famous one. Some Linux flavors come with graphical user interfaces, like Red Hat has an interface, CentOS has an interface, Ubuntu has an interface. Some of them don't. They just have the command line interface. So in command line interface, basically you have to type your command, and every single command gets executed. Yeah, that's the difference. And question 4, what are two types of software licensing? So you could put different names here, but basically we had open source and closed source, or proprietary, uh, something that is a property of a company that sells the license of using that property to. This one, I think, again, many people did this question wrong. What is another name for base 16 number system? This was somehow futuristic question. So some quizzes are like this to make you sometimes think about it or try to see if you know something from the past. I guess we didn't explicitly talk about this, even though many people did this correctly. So this was hexadecimal. We have, as I said, base 2 binary, base 8 octal, base 10 decimal, and base 16 hexadecimal. And say something interesting about question 6 was basically a repetition of one of those parts in your activity. So we wanted to know what you're really interested in the world of ICT, and with the activity and with this one, we got our answers. All right. Now this is the poll. Please ask questions. Any questions? Any questions? Yes means you have to ask question. Victor, Shao, and Gurmahak said yes. That means you have a question, unless it was a misclick. We have 20 people attending today's lecture. I hope as semester goes on and you guys get busier, I hope we don't shrink. Maybe 1 or 2 sessions if you're really busy, that's fine. For the activities and for the quizzes, you've seen there is a lot of flexibility, a lot of time, but for the lectures, I hope everybody can attend. So please try your best to attend. Let me see, we have something in the public chat. Misclick, okay. Gurmahak, thank you. It was a misclick. Was a misclick, Victor. No questions. Vitaly, thank you. All right. Wonderful. Okay, so if no questions, I'm gonna start today's topics. Let's see what we have. All right. I guess you see the slides, right? Somebody tell me if you see the slides. Who is that somebody? Okay, Ziffy said okay. All right. Uh, Today, as I said, we'll talk about some history and brief review of computers and most importantly, programming languages. So this lecture is trying to show you what possible languages are out there, and I have tried to briefly explain each of these programming languages, the strengths, weaknesses, the area that they are applicable. Are they still in use? If not, I didn't even put in the slide. So all we see here today is still in use, still significantly important in the industry, and they have commercial values. So whatever you see here, there is a chance you will get involved uh, sometime in the near or yeah in near future, sometime near future, obviously. So let's listen carefully and see what's going on uh, today. Also, we will see some algorithm, some pseudocode. What is the difference, if there is any? Programming code, and where did programming even started? And why do we even need computers? So this is a very fundamental question we will also try to answer. Um, what do we mean by low-level programming? High level, low level, what does it mean? Which one is better? Which one should I use? Which one should I avoid using? Is there anything that I should avoid? So many questions. Um, what is a compiled program? What is a piece of code that should be compiled so that you can be able to run? And what is the interpreted piece of code that you can run? Scripting. What is scripting? What is a script? What is a scripting language? What is embeddable, or in other words, embedded programs? Do we really need all these programming languages? Do we really need to know all these? This is another question, because there is so many out there. Even though to some extent they share concepts, even sometimes syntax, but there is a lot out there, so it might not be possible for everyone to know everything. So this gives you a direction on what programming language you need to start, and you need to get more information about. The activity that we will have is very simple, super simple. I'm so sorry. It's super simple for those of you who like challenges. There's no challenge here, guys. I'm sorry. This one activity is we have given you topics, simple topics in two different categories: algorithms and pseudocodes, and ICT past, present, and future. These questions are just a game. So please enjoy your activity of this week. This is simple. Just write whatever you want. 250 words. You will select one of these topics for each of these categories and write 250 words for them. So again, there will be no correct answer, but marking will be based on how deep you go, how deeply you think about it, and how you justify your answers. So please think about this. Is just an excuse to think about some topics inside any of these categories. But there is a reason behind this. Why this activity is so simple for this week? Because I wanted you to go ahead and there are links throughout this presentation. There are links that you can click and go to the official website of those programming languages. I wanted you to have time to check these websites and see what's going on for each of those. Uh, You might be familiar already with some of these programming languages. Mostly, I know people usually know C, usually know JavaScript. Uh, to some extent, in high school, you might know Python, which is very popular these days. But there are so many other languages that you don't know. Sometimes you haven't even heard of them, so you don't even know they exist. So this is the time to go check those official websites and see what is even this programming language. And that way you will figure out why and what is it good for, or you will say, okay, no, this is useless. I don't think I will be using this in the future, or it's not my priority. Okay, at least you know something is there and where to find the document, tutorials, and learning material for that. Where you can find, at least you know it's there and what that is good for, so that in the future, if you want to, somebody wants you to do a code with that programming language, or you might go to a company and see there are some codes that are still running, but like 10 years ago, some people wrote those codes in like Fortran. You don't even know what Fortran is. So this it's good to know, so that if you need to review some code or convert that code from one programming language to another programming language, at least you understand what that piece of code is doing, so that you can review and do these things. Sometimes happen, like they are not very unfamiliar. Sometimes they happen. Are we good so far? Not a Paul. Are we good so far? Any questions?
Yes means we're good so far, right, sir?
Pardon me, Vitali? What did you ask?
Yes means we're good so far,
Yes.
right?
Yeah, exactly. Yes means you're good so far.
Okay, okay, just checking.
Yeah, it means you're good so far. 50% are good so far. The rest, they either they don't care, or they're playing some games, or they're not even listening. I don't know. Still, we have, okay, not bad, 12 people. So, uh, GI, is this a misclick or you're not okay? If you're not okay, please ask your question.
Oh, I'm okay.
All right.
Oh, sorry.
Okay, good. Okay, thank you. And let's continue. Okay, so somebody invented something someday, which was a revolution. That somebody was Intel, engineers at Intel. And that something is this piece of IC, which is the first semiconductor based microprocessor. Each, like anything that is new to you, I have tried to explain. If I you see that I just said something and you didn't understand, please ask. For instance, what do we call a CPU? What is a semiconductor? Things like that. So I know these are things that you're familiar with. So for the things that I guess you're not familiar, then I have the explanation in the next slide, or like I will explain. So this is the first CPU that Intel built, 4004, uh, and this piece of IC was a revolution. What did this have? Actually, it was a, if you look at it now, it is just very, very simple, very trivial design. But at the time in 60s, it was a revolution. It was a 4-bit microprocessor. It had only 16 pin out. So compare this 4-bit to 64-bit processors that we have these days. Most of the processors that are out there are 64-bit processors. And I will tell you what this 64-bit means and what a huge difference it makes when you shift from 4 to 8 to 16 to 32 to 32 to, then to 64 bits. This microprocessor IC only had 16 pins, which is interesting. These days, you see microprocessors or CPUs coming with hundreds of pins, 200, 300 pins. So it shows the level of complexity. It was only running with a 740 kilohertz clock. What is a clock? A clock is basically a timing signal that plays like a rhythm. In music, you have rhythm. The drummer goes with the rhythm, and the whole music is based on that rhythm. Everything happens in between those hits, right? They they basically uh, do the timing. The drummer basically does the timing of that piece of music, right? As far as I know, I'm not a musician, by the way. Uh, clock is exactly the same. Clock plays the role of that drummer in the fascinating music of calculation in a processor. So you can imagine if you have a slower beat, that means you have a slower music most probably, because everything is slower because of this. The timing is slower. Clock is exactly the same. So with 740 kilohertz, meaning that uh, the beat is 740 multiplied by 1000 or 740,000 times per second. That means if you if your CPU is capable of doing its whatever it's supposed to do, in every clock, it can reach to maximum 740,000 tasks in 1 second, which is even not possible because many CPUs take many cycles to do a task. For example, you ask your CPU, uh, go ahead and print this character H, for example, whatever, to memory. CPU cannot fulfill this in one clock cycle. Some of them can, like it depends. But what I'm saying is it's very common that a CPU cannot perform a task in a single clock cycle. So the tasks that will be fulfilled is even less than the 740,000 tasks per second. Compare this to CPUs that are running in 2.2, 2.5, sometimes 3 gigahertz these days, and it means they are also many of them are also optimized to do many of the tasks, not if not all of them, to do many of the tasks in a single clock cycle. And with 2 gigahertz, you're capable of doing 2 billion tasks in a second. Compare data speed to this. It was not even long ago. It was like it was 60 years ago. And as it says, it took 8 clock pulses to do these fetch, decode, and execute. What is fetch? What is decode? What is execute? I will briefly tell you what it is. And okay, so this 92,600 tasks. Now you know what I'm talking about. So the 740,000 divided by 8 is 92,600 tasks or instructions each second. And yet it was a revolution at that time. it's good to know. You will see this somewhere next semester, or I'm sure you will see it. And it's the fundamental block diagram that you see in computer organization. This is basically what we call a computer. A computer is not your laptop, is not your smartphone, is not what you see. What we call a computer is a machine that can do this. Now, look at this very carefully, please. Now, you write the code in any programming language that you like, and you write your code in English. You understand what you're writing. Then you need something to either compile or interpret that code to something that machine can understand. This level is the assembly level. Guys, don't be freaked out when somebody says assembly language. Assembly language is as simple as this. You have limited number of commands. You can either load something from, like these are registered, these are piece of memories. You can load some data from some register to some other register or to some memory. You can save or load or add or subtract. Very limited. Like in RISC V, we have 32 instructions. So the whole possibility for you in assembly is you have to do your task with only using those 32 very primitive instructions. Add this to this, load this from memory to this register, save this from this data from register to memory. That's it. And this is the organization that a computer has. So from assembly language, still computer doesn't understand assembly language. And something is needed to convert this to machine code, zeros and ones. So every single line of this, these programs that you write in English translate into multiple lines. One single, so for a for loop is one line here, maybe for I equal to blah 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 blah. That for loop might end up being like 3, 4, 5, or whatever instructions, whatever number of instructions in assembly. This is not your task. Compiler does this for you. And after it converted to assembly, still because machine cannot understand this, you have to like the compiler generates machine code out of this, and this is the machine code. Now these zeros and ones, they are called opcodes. So they tell the CPU, they tell your computer what to do with what. They say, okay, this is data 1, this is data A, this is data B. Go ahead, add these two, subtract these two, multiply, shift right, shift left. Very primitive logic operations they can do. And what a computer does is they read, they are stored in a piece of memory called instruction memory, because these are instructions. And the computer goes and fetches each instruction one by one from this machine code, fetches this, then this has some data. So some data gets stored in the registers, providing that A and B, right? A and B. Then it goes to the ALU. ALU does whatever it needs. There might be some flags. The result of a subtraction might be 0. If the two inputs are equal, the result of a subtraction will be 0. So it will flag that 0 is on, whatever. And then another piece of memory, that is data memory, it writes the result to the memory if necessary, or if not, it just writes back to one of these registers. These registers, so this is what we call a computer. Any machine from old days, 10-ton giant mechanical machines until today's smallest smartphones with a CPU that has only 2 nanometer feature size CPU is doing the same thing. They just get more complicated and more complicated and more complicated, but the concept is the same. And this part is what a compiler does, converts your English code to machine code, and then the rest is, if you're writing in a high level language, also operating systems gets involved here. If not, it just this code gets fed to the hardware. That's why it's called bare metal. We'll talk about it. This is bare metal coding. If there is no operating system involved here, it's called bare metal coding. And then this gets executed. The standard steps for basically running each of these instructions is fetch. It means the instruction is fetched from the memory. The hardware fetches from there, and then decode. Then decodes. Okay, what does it mean? It decodes what it means and then executes. So ALU executes whatever that code was supposed to do. Registers. So ALU is a piece of hardware. It can be implemented using, well, it used to be implemented using giant machines with switches, vacuum, those vacuum, what you call it, those vacuum bulbs, very huge things. So it used to be, this part used to be implemented with that. Since 1968, it is being implemented on semiconductor. So implementing on semiconductor shrinks the size in a scale of millions, tens of millions. So those giant machines now are very small, 1 millimeter by 1 millimeter chip maybe. Registers are a piece of hardware. You can imagine these as shelves. These are shelves. You put your real things there, and your things are 0 or 1, just the data. A register can store 0 or 1. We have very limited registers, sometimes up to 12 or up to 20 registers. And these are inside your CPU. So this part and this part is inside your CPU. Data gets from the memory, data is loaded here, then one by one it reads and executes and writes to the memory. What is memory? Memory is a larger scale of a very, very, very super larger scale of these registers. So you can have billions of these registers in your memory, but basically they're the same thing. So as you know, machines were very, very large, but the machine that this guy is working and the machine and your cell phone basically share the same concept, and that very same concept is what we just went over. This is reading from fetching the data, decoding the data, and executing data, but they are done within different machines, and because they were using bulky devices at that time, wiring and everything, and nothing was integrated, they ended up having machines this big, for example, for computation. Now this is a picture, NASA high-speed flight station computer room. So this must be somewhere that people do calculations, very tough calculations, right? This is NASA flight station computer room. Yet, it's funny, there's no computer in it, and people are computers basically there. So people are computers. Well, kind of, we are reaching to the point, why did even people invent computers? What was the problem with people? So this lady is working there fine, and in 1960s they sent Apollo to the moon. Since then nobody has been to the moon. So what went wrong? This is a big question. the starting point of all this was a machine called ENIAC, Electronic Numerical Integrator and Computer, in 1946. You might have also seen a Turing machine, a machine that Turing designed and and during World War II to I think the movie's name is Enigma. That was something like this also. So these were the pioneers. This was a more basically a more developed machine at that time. And the interesting thing about it was that there were six women. They called them ENIAC 6, six women, not a single man, working here. And these six women, without using any programming manuals or anything, were able to program this. And this machine was designed to do some calculations, some solving some differential equations. So imagine every week their boss would give them okay, now this is the equation that you need to solve today, and they had to go break it down and change the wires to create the coefficients of that equation, right? And do things, and this machine broke every 15 minutes. So some of those workers, one of these women reported that they had problem with this machine every 15 minutes. So uh, they had to fix some part in 15 minutes, and there was the longest time that this machine worked was only 5 days. 5 days, imagine. So if they were lucky, they could keep it running for 5 days. Now, why even bother? So that machine was famous at that time. It was a huge revolution. Everybody was talking about it. But for a machine that problematic, and before that, people were doing calculations that could send satellites. NASA was sending satellites at that time. So what was wrong with it? Why did even people create this, and why did this become a trend? What do you think? Why do we need computers, guys? Why even this a computer with this level of inadequacy and inefficiency and problem? Why it wasn't news at that time and people praise those who invented this? Any idea? Public chat to save time. Why don't you talk? Guys, let's talk. Tishdeep, thank you. Vitali says, uh, mm, uh, no, Vitali doesn't say anything. All right. So to save time, yeah, exactly. That's a very good answer. So now look at this. I tried to give you an analogy here. So we have two mechanics here, Alan and Alex. They're two mechanics with two completely different profiles. Alan can fix an engine problem in 5 hours. Alex fixes the engine problem in 2 minutes. However, the difference is that you have to train Alex, and training will take about 100 hours. But Alan is an expert. He doesn't need any training. Doesn't need any training. And now the problem is, imagine a maker, Honda, for instance. Let's say Honda. Honda recalls 5,000 cars for a problem, for an engine problem. Okay? Honda recalls 5,000 cars for an engine problem. And you're a manager at Honda. Which one of these people would you give the work to? Let's see. Let's have a poll. Alan is this guy, Alex is this guy. Which one would you give the fixing job to do? Let's have a poll. Alan or Alex? And I have to A, B, C, D. A, B, C, D is Alan. B is Alex. Let's see. Go ahead. Quite a tight competition. 5 people said so far said Alex. 2 people said Alan. We don't know which one is correct yet. Okay, go ahead. We need more people to reply. People, it's fun. Just look at Alan. Just look at Alex. Don't you enjoy this? It's fun.
Sir, I have a question.
Yeah, go ahead.
Is it a one-time use or like every time?
No, this is a one-time project. So we are going to fix 5,000 engines, and we want to know if we want to give this work to Alan to do or Alex to do.
I see. All right.
Which one would you choose?
All right.
We have more Alex than Alan. We don't know which one is correct. Okay. 14 people replied. Thank you very much. So I'm gonna ask Bijoy if you're here. Bijoy.
Yes, sir.
Yeah, you said Alan. Why did you say Alan?
Because he doesn't need any training. Right? The other one needs 100 hours of training, but he can't
Okay.
fix it in 2 minutes.
Okay.
Yeah. So Alan saves time. Like if he needs only 5 hours, but he doesn't need any training. But he saves training hours. For training, 100 hours in 2 minutes. So 1 hour is 60 minutes, and for 100 hours it's like 6,000 minutes or something. For he wants training for Alex. So I think it's better that Alan is good.
Okay. Yeah, to some extent it is true, but then you think about, okay, I would give it to Alex, by the way. Why? Because I have to spend 100 hours training Alex. Yeah, fair enough. Alan doesn't need that. But after that 100 hour passed, Alex will fix in 2 minutes. 2 minutes multiplied by 5,000. That is 10,000 minutes. But if I give the work to Alan, so overall 5,000 multiplied by 2 minutes is 10,000 minutes plus 100 hours is I can't calculate right now. But now imagine 5 hours multiplied by 5,000 cars. Isn't it much more than what Alex spends fixing these? I think if you think about efficiency, your time, cost, and everything, you should give the work to Alex because it is difficult. It is very difficult. You have to sit down, teach Alex even the basics of engine, how an engine works, everything, every single detail about engine. It's cumbersome, it's boring, it's time consuming, it's not good, right? That 100 hours is hell. But after that, he's gonna fix each car in 2 minutes. So 2 minutes past, car is fixed. 2 minutes past, car is fixed. Isn't this concept similar to you when it comes to doing the task by yourself as an expert? You and I are like Alan. We are experts in what we are doing, but it takes a lot of time. We are not that fast. We are not as fast as computers are. But Alex is a computer. It's like a computer. It doesn't know anything. It's dumb. It's dumb. It doesn't know anything. You have to teach every single detail, and that's the programming part. You have to program Alex so that he can do the job. But once the program is done, it's gonna do the whole task of fixing the car in 2 minutes. Isn't that amazing? This is exactly why people invented, created, used, and developed computers, because they are faster. They're dumb. They don't know anything. But imagine, are you gonna give the job to Alan, which is you and me in this example, or give it to Alex? I want to spend 100 hours programming, and then I want to go on a vacation. I want to sit, play game, watch movies, and I want my computer to do my job, right? So that is the main difference. Why people needed, invented, and this computer ICT is almost forever going on. Okay, I hope we got this, and I hope we do this. Like now, you guys, as you people, ladies and gentlemen, as programmers, you will be able to develop more efficient programs in the future. So spend some time, spend 4 hours, 5 hours, 10 hours on a program, and let that program do whatever you want it to do by yourself. That's the way professional people do stuff in this area. Okay, let's see some beginning of. So in 1951 was the beginning of now computer logic designer. Then 1962 people started using some of these. So 1962 was the computer coming into airline. So people were realizing, okay, now these are doing things faster than our employees. So why not employ these machines and let people be experts, but let people not do the labor. Let people be experts and program these machines to do the job. So it became more and more popular in late 50s and 60s, and we reached to IBM's first personal computer that at that time was a revolution. And I remember my dad learning this. I remember once he came home, he was so excited because his company was offering a course, and they had, for their whole organization, they had one or two of these IBM machines with large floppy disks and all that. And he was very excited. He told me, I'm learning computers. I said, what's computer? I think I was 10 years old, 10 years old. And he was very interested. Actually, it was in 1981. If you're trying to calculate my age, uh, it was long after that. It was invented in 1981, and it took some time until it became popular. I'm 36 years old, by the way. And then we go to, oh my, I think my picture got in the way. There is a lot of hardware. The good news is that there is a lot of hardware. There is a lot of option to choose hardware, and that at the same time is the bad news, because you have to know something about hardware to be able to choose from, to be able to program for. It's not that always, well, to 95% maybe, unless you're doing system programming or embedded system programming, 95% maybe you're good if you know what, if you don't know much about hardware. But really, it's a turning point. As soon as you realize you know something about hardware, how this code is getting executed, that's the turning point for coding. So can you answer why in C programming, for example, we have I equal to I plus 1. That's when I want to increment I. I equal to I plus 1. Or I can say I plus plus. Everybody said, like, not everybody, somebody know that and say, okay, I will definitely choose I plus plus wherever I can. Why? Because I plus plus is faster than I equal to I plus 1. Unless you know how it is executed in the hardware level, you know something about those registers, you will never understand why I is equal to I plus 1 is slower than I plus plus. You will never ever know that. And there are things like that. So knowing hardware helps. There's a lot of options. I encourage you to always revolve around hardware things, or at least basic concepts. We are, and we will also cover some more in our slides. But from now on, it is software programming. Software, the first software was developed in 1842. By software, we mean the piece of code that with the pillars that we know these days. I'll talk about them. But it was basically developed. This was a woman. Uh, this also was a lady that developed this, and I think let me see some slides. Did I miss anything? No. And this was a lady that were able to write this for. This was for ship navigation. So this algorithm was able to calculate, and it was running on a physical machine that they had at that time. But what was interesting about this program that was considered the first computer program ever was that it had three concepts that all software programs have. So when you're programming, you will always need to think about these three pillars and implement your code using these three pillars. The first one is sequence of your code. What comes first, what comes next, and what is the sequence of running my program? Why? Again, you have to know how the hardware works. Didn't I say uh, every single line of code gets executed separately in your computer, and then the computer goes and reads. After it's done with the first one, it goes and reads the second line, the third line. That is exactly why sequence is important. You cannot go out first and then put on your shoes, right? In your program, you have to think about the sequence of things that's going to happen. Sometimes it's just very easy. Intuitively, you know what comes first, what comes next. But sometimes it can be complicated. You need to do it right. For the second one is the conditioning. So this is a decision you have to make. When you reach to a point, you have to make a decision. If this is this, I will do this. If not, I will do that. This is the second pillar that existed in that program, and since then, it is still the second pillar of programming. And the third one is looping. You have to be able to repeat a piece of code if you want, and that's called looping. So this it's kind of ancient, 18 something, man. A lady in 18 something wrote this. It's mind-boggling. And more on women that did fundamental job to the world of software that we live in, and the easy things that we do now easy, but at those times it was very difficult. Grace Hopper was one of those. Grace Hopper, she was a computer scientist and also in the United States Navy. What she did was fundamental. One of the most important things she did was invention of compiler. Why? I showed you assembly code, right? Assembly code. People in old days, in 60s, late 60s, 70s, they were doing assembly. So they had these limited number of instructions and they were trying every problem that they had to solve it using these limited instructions. And it was for the first time, and nobody could understood those. Like it was, you saw assembly is S SBR, LW, SW, something, something. It's not very clear what this program is doing. So for the first time in the history, Grace Hopper insisted on having a language that is English so that everybody understands, and then she personally invented and wrote the first compiler that could convert English to machine code. And we basically all compilers to this brilliant lady. And many more. Now in other slides you will see she has done many more. So for the first time for the first time in her job and her computation, they had this large computer for their Navy calculation stuff, and an engineer for the first time discovered that a bug intervening between two relays. This is a piece of document in a museum. Relay 70, this bug was there, and this was the reason that calculation failed at that time, and this was the first time word debugging was coined. Debugging means taking real bugs out of your hardware, but we have borrowed that concept and we are using in software. That means taking out your mistakes from the logic or the piece of code that you have. And yeah, this is interesting. Let me see, guys. Is this getting boring or no? Let me see. First, let me check. I have something of public chat. Alex just need one time away. Yeah. It exactly. Dashdeep said that. Back to our Alex and Alan discussion. Alex just needs one-time investment. Exactly. You invest on that, and you're good to go after that. Guys, please talk. See, now I don't check public chat frequently. I don't even see it. Please, it's fine if you're right there, but if you want to say something, please just feel free to say. And all right, are we good so far? Let's have another poll. Is this boring? Okay.
Only a little bit.
A little bit. I know. Don't worry. We will reach to software part soon. You go ahead and reply to this. Some people got bored. You want the truth. I want the truth. Yeah. Abdullah, I want the truth. I think your answer is I see. Well, how about ladies? How about ladies? I think you should be motivated. Now, all these amazing ladies doing these amazing things. Anyways, okay, let me publish the poll. Let's wrap up this this history part. I knew it would be boring, and this was the Google Doodle in 2011 for Grace Hopper's birthday. Another example, we have Margaret Hamilton. You probably know her or you've heard about her. All these are the assembly instructions. Assembly instructions. She had to sit down and double check. Some of them she wrote to send Apollo to the moon, and it was successful. So if you're interested in this, please go ahead and check. How many? Okay, I need to know. I need to know this. Please, male, male, female. Let me know how many women we have in our class. Obviously, if you're male, okay, I can add item other. Male, female, other. Guys, it's go ahead. I want to know how many women we have in this class. 7 to 3. Wonderful. See, still today, still we have more men in ICT than women, which I think they have done great job, and we need more. So it is 3 to 11. 3 to 11. So these 3 women should really be proud of themselves. One fun thing I wanted to thank you so much for the poll, guys. One interesting thing is that if you didn't know, it's fun. You can create your QR code, or barcode. I'm just gonna show you here. It's fun. If you go to this website, you can type your text here, whatever you want, CPR 101, and it converts that to a barcode or QR code. QR codes are more interesting. They occupy the same size, but barcodes are not like that. Oh, by the way, let me show you. If in a barcode you repeat your text, or if your text is a large text, now look at what happens to your barcode. It gets larger and larger, but that doesn't happen with QR codes. This is just a break. We are these slides are we are in a break. Now look at this. I want to create a QR code for this. It doesn't get larger. The data inside that just gets more condensed. See, now this create this, and it's fun. You can do this for yourself at home. Just wanted to show there is this possibility. Now, programming languages. Starting programming languages, as we discussed, very basic concepts, language structures, instruction sets, and many other things. As compiler, we said, developed in from 1940s to 1960s, mostly ENIAC 6, those 6 women, and Grace Hopper. And then early languages, still some of them were good enough. These are not all the early age languages that we have. We have selected only those ones who still exist. So if they lasted for 60 years, 50 years, 60 years, it means they were good enough. One of them is Fortran. Fortran was basically good for it's still good for basically multi-parallel computing, and wherever it comes to significantly high processing demand and calculations, like scientific calculations, floating point calculations, precision, stuff like that. This is good, and it is still up to date. If I click here, I have put, yeah, these are links I have put for you. If you're interested, you can just click and check the website. Check each of these websites. This is the task I want you to do. This is up to date. So still there are people using Fortran for some purposes. What is the purpose? You can have, there are a lot of tutorials. It introduces you the compiler. It gives you the open source compiler for Fortran. You can install. You can do some test programming and stuff like that. It's still a highly accepted program for scientists, for benchmarking. You've heard from time to time they say, okay, now this is the most powerful supercomputer created in China, created in Norway, created in the US, in Europe, in Canada, wherever. How do they know? How do they even know this is the fastest? These are there is benchmark programs. You have to run the exact same program. They are calculation intensive. They run these programs on different machines, and the fastest machines will be the most powerful machine because they are running the same program. But Fortran is one of those programs that people use for benchmarking as well. And parallel programming. Now you can imagine, I just want to give you a sense of how things are going in real world. If it is a parallel programming, so in the previous one you had to fetch one execution at a time, but then like if you have two cores, like if your CPU has two cores, core 1, core 2, now it is capable of fetching two instructions at the same time. Many complications we will have here. If these instructions have dependencies, then there must be a way to solve these dependencies. For example, if instruction number 2 is using the result that instruction number 1 is calculating, the result may not be there for the second instruction. What should I do there? These are things you will see later. You will see pipelining, later you will see parallel programming, stuff like that. But just keep in mind, in parallel programming, we literally duplicate our hardware, but even though it becomes very fast, much faster. And by the way, this is called multi-threading, different threads. Each code feed is thread. Multi-threading in parallel programming, and it has a lot of complications you might be interested in later. So Fortran can do this parallel programming also, or multi-threading, as can C++ do. Also, another language that still exists, it's COBOL. It's mainly used in mainframes. And what is a mainframe? Mainframe and cloud. They cannot be used interchangeably because they're significantly different. By the way, I have taken this slide from this reference. This is the mainframe. This is just a mainframe that serves multiple users. Multiple users can connect using a local area network, for example, or whatever. And this is the mainframe serving other things. It's basically kind of server. But cloud is all these mainframes and all those infrastructures that we don't know where they are, what they are. We have no idea, but we are just connected to them through the internet. This cloud, as you can imagine, is much more powerful and resource rich than mainframes, right? These mainframes have limitations, but cloud doesn't. So it's still in use, this language. If you go to work in a bank, for example, you may see this, and still alive, still going on. In 1970s, C was created. The reason C was created and invented was that people were tired of doing assembly code. And they wanted to basically write their codes in a way that is more structured and more understandable, and therefore could be debugged more easily. And that's where C came in. Why do we say it's structured? Because in C, you, for example, you write an if-else condition like this. By the way, this shoot in the foot is a term people use, programmers use, because many times happen that you shoot yourself in the foot by writing a program that is supposed to do something but is doing something else. It's just a joke. So this is a structured way of doing it in C. But before that, people used to, even in assembly, it's like that. In assembly, you write a tag and then check something. You check, for example, here this is the exact equal code to this, but you are everybody has been forbidden from writing this. Why? Because this creates a mess. Go to creates a mess. This go to tag creates a mess, but it does the exact same thing. So a condition is checked. If this is false, then it takes the flow of the program to where, to this tag. False is here, so this gets executed, and then after that there is no code. But if it is not false, then this will not go there. This will go here. This will do this shoot, and to be able to not to run this anymore, because we have already now executed this because this was not correct. We go to bypass, and bypass is where the program ends. You see how complicated it becomes and how messy it can become if you're writing a code that has like 5,000 lines of code. It just becomes crazy. Same thing for for loop, structured for loop in C, and now compare that to a go-to version of for. Now, if first you set I to 1, okay, fair enough, we do the same in the structured form, and now check conditions. If this is true, go here. If this is not true, then do this, increment, go back here. See how complicated it is becoming by adding goto. So goto is a big no-no, even though you can use. It's not. It is syntax-wise correct, but it's a big no-no. You shouldn't use. You should avoid it. It's a big no-no. So let me see if we can have a break. I know this today's lecture is a little bit probably long. Do you want a break now or later? If you want a break now, say yes. Okay. Yes, people want this. We will have a 15-minute break. We'll come back at 1:30, guys. We'll see you in 15 minutes. EST time, it will be 1:30 p.m. EST time. We'll see you then. Very good. Okay. Who's here? Are you here? Yes or no? Just 8 people? Okay. I think we have enough people to start. So, in the this was what happened with C. Basically, C gave structure to programming and avoided so many issues that would otherwise exist. but still it wasn't enough. Comparing C to C++ that became available in ATs, if you compare that, it's comparing Play-Doh to Lego, for instance. Object-oriented programming is mainstream, and two things happened in ATs which still, not one of them, object-oriented programming is still around, but not databases that much, because there is a reason. Object-oriented programming, I'm going to give you an example. If you have a car, you have a car, and if you want to move your car, I give you a car and tell you that it doesn't have an engine. It doesn't have an engine. But if you want to move this car, you have to find a way to move it. You put it in another container and move it. That is the type of car that C programming gives you. It gives you the variables struct. You have a student, for example, struct in C, but that student cannot read, cannot write. That student is blind. It cannot do anything. And if you want that student to read, you have to use functions, read functions or something like that, and send that student to that function so that that student is able to read. But it is not like that in object-oriented programming. We define classes, and those classes are fully capable real-world objects. In object-oriented, you have a car that also has an engine, that also has a brake, so it can do everything that you are expecting it to do. So there is a big difference between that. Basically, object-oriented programming created a big difference. We were able to define classes that could have member functions. Member functions could do a lot. And now our objects that were instantiation of those classes could do things by themselves. You didn't have to carry them and send them and put them in another carrier like a function to give functionality to those things. So it gave, you will see more in C++, object-oriented programming, and other programming languages that are object-oriented like Java. SQL also became a big thing at that time, relational database management systems, because at that time, look at this, at that time, this didn't exist. Basically, people put their code wherever their data. Imagine there was like a name of employees of a company and their information, things like that. There was no structured way of saving this data, and everybody could put it in a file, in a text file somewhere. Any program could access that, could change any. There was basically no structure. So relational database management systems, SQL, and later SQL Server, like these days for web stuff like that, they created a structure for this data to be saved. And why this said it's relational? Because each piece of table, each piece of data is related to another piece of data. So you can see here, for example, in C++, this simple C++ coding example, it is now more difficult to make mistakes in C++. But if you make a mistake, that's going to be a huge mistake. Typically in C++, you have like memory management problems, memory leak problems, stuff like that. And this part is SQL. SQL, it creates, so basically you create systematically. You have a standard language now to create these databases. You create tables, you define columns, you put data in those, you do sorting, you do searching, and all those stuff are more systematic in the ATs. In the 90s, it was the era of GUIs and event-driven programs. So previously, programs couldn't basically respond to an event, and that event could be anything from a right click, mouse right click, left click, pressing a key, or any other event that could be generated externally or internally. Um, Programs couldn't basically respond to those things, and there was the graphic was not there and all that stuff. So in the 90s, the program languages were developed that were able to somehow, to some extent, fulfill this. For instance, Visual Basic, which nobody liked at that time, and then it became outdated. Almost nobody uses that because it had different syntaxes for every edition of that, and it was not a good experience. So people didn't like that. Python, one of the most successful, and today is the most used programming language, was initially developed in 1991. What is the strengths of Python? It's a question from you. Those of you who have done some Python coding, what do you think is the strength of Python? Why is it so popular? Is it becoming so popular? Any comments? People. So I will tell you, the Python has very rich library, and it is very easy to read. It's almost English language when you're writing the code. So it is very popular because you can read and write simply, basically write code and read simply, and using extensive libraries, you can almost do anything using a library that you don't need to worry about. Another amazing program language is Java. Java is also it's been very successful, and people also use it these days, and many backend designers use Java. Does anybody know what Java is famous for? What is the main feature of Java? Why do people use it? Why do people like it? Java is there's no answer. Are you sleeping, people? Java is famous, and it was widely accepted at the time of when it was first when it came to market, because you could use it in any platform, and by platform we mean hardware and operating system. So you could use it on every machine. You didn't have to change your code or change compiler or anything. How it worked? It worked like this. So you wrote your code in English. It didn't compile to machine code, as opposed to what takes place for C++, and this type of languages. It translates to bytecode first, and that bytecode then needs another machine called Java Virtual Machine, and that Java Virtual Machine basically creates the machine code specific to any platform. Platform is hardware plus the operating system, and that way basically people could just write their source code without worrying about, will this run on my Windows machine, will that run on my Mac, and will that. So this is a cross platform. Basically write it once and run it anywhere. Why? Because of this intermediate level that they introduced. So Java Virtual Machine. you need to install this on your computer, or even it can come with the program, so it can be embedded in the program. So as soon as you download the application, Java Virtual Machine comes with that, so it can execute, and you don't have to do anything. So this was a revolution that Java created. So there was no problem you running this on different platforms. JavaScript, again, 1995. You see, all these are happening. Like Java is happening when? Java is happening at the time that people are now having more option with their PC hardware and PC operating system. So multiple operating systems are there and multiple hardware. So Java was created so that you don't worry about those platforms. And then JavaScript is also the time 1995. In 2000, .NET revolution started. So everybody was talking about internet, websites, stuff like that. Java was one good choice. So people wanted to use Java to create their web pages, interactive web pages, obviously. But Java, with some browsers, it had problems. So JavaScript is basically another version. But it's really not Java. If you want to know the differences, is there anybody here that knows the difference between Java and JavaScript? Please, let's have a discussion. If even if you guess something, or you've heard something, or you just guess something, let us know. Public chat. Why do you?
I believe Java is more simpler than JavaScript. I don't know exactly.
Good guess, but you have to say the other way around. JavaScript is more simpler than Java. There are yeah, but good guess. Good to begin. In the next slide, I have.
Like I've used both, and like what I found was that Java was easier than JavaScript.
Java was easier. Yeah. But in general, like if you want to talk about the differences, Java, you have to compile Java, but JavaScript is interpreted. We will now, next slide will tell you what is the difference between compiled and interpret, compiler and an interpreter. Java usually used for backend, so for large programs that run in the backend, you can usually use Java. But JavaScript is just mainly for front end, and that's for making web pages interactive. Like if a user does something to manage all those events, to change the style, interactively change the style of a page, add, remove text and content. All these things are JavaScript is responsible for doing these things, and so as you can guess, it runs only on a browser, or in .NET or in Node.js machines if it is on a server. But Java can be executed on a browser, or if you have a JVM, you just execute it. For JavaScript, you need a browser. And the syntax of Java is similar to C++. Syntax JavaScript is Java similar to C++, JavaScript similar to C. So that's why I thought maybe this makes it a little bit easier, because like C syntax is relatively simpler than C++. And then for development, it requires its own kit. But JavaScript, you can just simply open up a notepad and write your code. And you can create various applications, desktop applications, server applications, or whatever application. But JavaScript is mainly for web pages. Another important thing is interpreter versus compiler. There is a difference between interpreter and compiler. Those who have programmed Python, they know that every single line of code they write, they just see the result. If they're adding two numbers, they can immediately see the result. That's the job of an interpreter, because Python is a programming language that has an interpreter. Interpreter takes each line of code that you write and translates that to machine code, executes it, and shows you the result. But it's not the same with compiler. Compiler waits for you to write the whole program. C is like that. C++ is like that. You write the whole program in different modules and create everything, and then compile. Then compiler goes thoroughly, reads all these codes and everything you have written, and then links them and creates an object code, an executable code that you can run. So which one is better? Which one is more faster? Which one is like? What are the pros and cons? Obviously, compilers are faster because they compile the whole thing. They have a bird view on your code, what you want to do. They know everything because you've written a complete code and now the compiler is compiling. But interpreter is not like that. Interpreter just sees the line of the code that you have written and whatever you have written in the before that line of the code. It doesn't know what will happen in the next line. For that reason, interpreters are more flexible. So, for instance, let me show you interpreters. I will show you the slide. In an interpreter, you can, for example, you don't need to worry about type of your variable. You can define a variable, you can store a name in it, and then you can store a boolean in it, and then in the same variable, and then you can store numbers in it. So no worries. They give you more flexibility. Interpreter based programming languages versus compiler based. So you have to be more careful with compiler based programs, but they're faster, and I can say they're more efficient in terms of running on hardware. We talked about Node.js. Node.js is basically what they run on they run on server, and JavaScript codes can be executed on. You'll probably see more on this on other courses in the future. And after JavaScript, PHP is also another programming language that you will see. What PHP does is basically it runs on a server and on a web server, and it just waits for HTTP request queries for all those queries. You send your query by, for example, you're doing online banking. You put in your numbers. You're doing an e-transfer, let's say. E-transfer. You put the name of the person you want to send the money to, and you put the amount, everything. You click. Now you click do this transaction. That's a query. It is if the backend is running on PHP, so it receives your query. Then it creates it. Its responsibility is to create an HTML page and send it back to you. So it compiles everything, communicates with the database, sets content, style, everything, and then sends back the HTTP to you. So if somebody wants to work on web servers specifically, PHP is a good option. So to give you an idea of different flavors of these programming languages, these are some examples you can see. So for instance, Python is really simple, very close to English. The same code has been written in Java, C#, JavaScript, and PHP. 2000. Now, object-oriented programming is the mainstream, and also now also people like those programs that are scripting languages, meaning that You write a line of code in your Windows. If it is Windows PowerShell, you write it in terminal and whatever. So you write a line of code or a couple line of codes, and you want them to be executed. So these are called scripting languages, and these are becoming mainstream. Plus, object orientation as a concept is important. 2010 plus, then now we have mobile and tablets. If you want to see a safe design, Roost is well, my friends believe Roost have a bright future because it is safe. Basically, if we want to compare to shooting in the foot, in Roost it's almost impossible. You can shoot yourself in the foot. So it is. You might take a look. That's why I've put a link here. This is the official website. Also for Java and Python, please check the links later. Parallel programming GPUs, graphical processing units. These are rich. They require rich parallel processing. So these are pixels of a computer. So right now you're looking at a lot of white area here. All these areas have the same code. So parallel computing, each of these parts of the display can be controlled by some part of these cores of these GPUs, graphical processing units, and because everything is being repeated, so there is a lot of white space. Parallel processing is efficient, especially for GPUs, and again, big data, Java, Python. You see a lot of libraries for Python these days, for big data, for AI, data manipulation, and stuff like that. Also, people do it with Java. Distributed processing. Please check. You can check. This slide has a lot of links, so just check them. For the popularity of programming languages and all that stuff. I think we have in public chat. Do we have anything? No. Okay, going back to these slides. We also have markup languages. They are not programming languages, people. They are just a means to decorate your content, basically. So HTML, CSS, XML are one of those. XML is for indexing things in a location, in a file, or things like that. So these are not programming languages. They do not get executed in your computer, but rather they are some symbols, some things added to the text to give it a style. And this is what we have. So you cannot say I've programmed my website in HTML. HTML is not a programming language, right? It's just a markup language. History of computers. So we have two types of, again, another interesting thing. You will definitely complain about your compiler, about your programming language that you use. You will definitely face lots of problems. That's the nature of this, but practice makes perfect. Programming architectures. Now, another category we can use, other categories that we can use to categorize these programming languages are these: interpreted versus hybrid versus compiled languages. We talked about the difference between compiler and an interpreter. High level versus low level, general purpose versus domain specific. And obviously, as I said, you can write bad code using all of these. Roost is really good, by the way, for managing these problems. And high versus low level programming languages. So if in the beginning I said that old days there was no operating system, even nowadays on some embedded level, we have microcontrollers that do not need. The application is simple, so simple that you don't need an operating system. There's no much concurrent things going on that you need an operating system to manage those, do time scheduling or memory management, stuff like that. So these are simple. There's no need for operating system. Basically, you use C or C++ to Java also to write programs for bare. This is called bare metal. Why? Because you are burning that program directly into the hardware, and there is no operating system there to get involved. So your code is basically both the application and the operating system for that piece of hardware. And high level languages, they run on an operating system. They basically communicate with an operating system, and they don't know much. They are blind to hardware complexities, so they don't even know how this thing is being done. um, this is the example I wanted to show you. For instance, if you write this in Java, which is compiled, you will get an error, or C or C++. You cannot change the type of the variable. Now you're changing the type. Here it is this string. It's a collection of characters as it has been defined. The value, this is fine, but if you want to pass 34, you'll receive an error when at compile time. Or uh, like Visual Studio is smart enough to tell you right there. It will underline it in red and will tell you it's not acceptable because name is a string. But in dynamic typing, in the interpreting form, this cannot happen. It actually, this is fine. Like they let you do this, and in the background, the type automatically changes or gets duplicated. Uh, Domain name specific languages. There are some languages that you cannot use as a general purpose language, and they are domain specific, like PHP, we said. So PHP is just to run on a web server and is responsible to get the query, create another HTML as a reply to that query, and send it back to the client. You cannot use PHP for like creating a Windows application, right? For example, things like that. And command language are basically interpreters. Why interpreters? Because in command line you write a single line of code and that gets executed. Uh, Anything that you write on Linux command line interface or PowerShell, or uh, basically uh, the 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 console that applications give you to run your programs. For instance, we have in Visual Studio, you can open a command line and write your code there, and line by line it gets executed. And we have data-oriented languages as SQL. So these are basically these are there to organize uh, your data, your big data, your data, or whatever. They are there to store and organize your data and give the data back to you whenever you want, the, in the in the in the very optimized fashion. Um, so we talked about this statically typed and dynamically typed. I said statically is when you cannot change the type of the variable that you've defined, but dynamically typed, so that happens in the compiled version of programming languages, and dynamically is in interpreted languages, and they can automatically take care of this. Hybrid is somewhere in between. So for instance, in Java, uh, you first compile that to the bytecode, and then it gets interpreted by another uh, virtual machine, for instance, in Java. Uh, So here is a summary of what we have discussed. We have high level domain specific languages. High level means an operating system is involved first, and domain specific language, it means that is that can just be used in a specific domain. Uh, an example was PHP or JavaScript, specific domain for web. But other than that, other programs are general purpose languages you can use to create apps that can run anywhere on any platform. Uh, we have TypeScript and JavaScript here, so there is a difference. And also we have Groovy, we have .NET, uh, things like that. So take a look at this table later on. TypeScript is a completely independent and different object-oriented programming language. It's good for creating web apps, and it's much vast and much more capable of doing things than JavaScript. So you can take a look at that. Groovy also is uh, Java can be a subset of this. So Groovy is also a programming language that you can use the same syntax as you use in Java, and it gives you more flexibility and more efficient data. So for example, I have taken this from this link. If you compare the same code in Java and versus here in Groovy, it's much shorter and more efficient. .NET was also very famous in 2000s. So it's a free open source platform if you want to write apps for Windows based systems, whatever that runs Windows. You can, if you want to write an application, .NET is a good framework for that. You can take a look at this later. Also, there are links here for e-learning people. You can use your LinkedIn Learning. You can use your LinkedIn Learning. It is free through Seneca. You just need to click on this and log in through your Seneca credentials, and you can access thousands of wonderful lectures and sorry, courses. So please use that. At the end of the day, programming is an art, and there is no single way for writing programs better, except for practicing and seeing multiple well-developed codes and trying to mimic those concepts. And someday, who knows, we might be able to be able to write very efficient programs. We also talked about non-programming languages, HTML, CSS, and XML as markup languages. Some vocabulary here we have. Just to let you know, this is for you will see algorithm or pseudocode. I have used algorithm and pseudocode interchangeably here. Typically, algorithm is something that you draw. So it is you draw different blocks. They have different meanings. Some blocks are computation blocks. Some of them are display. Some of them are input. Some of them are conditions. Stuff like that. So you draw and you write what happens in each block, then start implementing each block separately in your code. Pseudocode is also like that, but you don't draw. Usually people don't draw anything. They just write step by step. They just write step one, one sentence. I'm going to do this. Step two, I'm going to do this. Step three, I'm going to do this. So basically here, even in your activity, what we mean by algorithm is pseudocode. They have been used interchangeably. We don't want you to draw anything. And when we talk about pseudocode or algorithm, you write a step-by-step operation of how to solve that problem. An example is here from this website. Step 1, do this. Step 2, do this. Step 3, do this. Uh, this is not a language. It cannot be compiled. It cannot be interpreted by any compiler or interpreter. It's just understandable for me and you. And my mouse is stuck there. It's just understandable for me and you. You give the solution to a programmer or program it yourself. But this is a level between um, problem as in its totality and the program. Step by step you can implement these. Okay, finally we are at the end of our today's long lecture. Now I want to know, let's keep it here, and I want to know if you have any questions. Please go ahead and let me know if there is any questions. Oh, by the way, this is the activity. As I said, it is super easy. It is. This is the activity. Just 2 questions. You will write a say about these, and this is the instructions for activity of this week. 2 categories, and in these 2 categories you will need to select the topic and write about that topic. This is all about the activity. Okay, any questions so far? So take your time and check those links for different programming languages. I'm sure you will find plenty of useful stuff. Some of them do not even have an official website because there is no organization or group of people that supports that. But for many of them, we have their official websites, and you can find plenty of material, learning material, their compiler, their how you can write a program. Some of them even show you some IDEs you can install and start writing programs. But Visual Studio typically supports all those. You just need to read in those websites how to configure and how to install the compiler or the interpreter in Visual Studio to be able to write that code. Okay, thank you so much. Now we have one presentation. Thanks to Naveen. I'm gonna run his presentation here. I think you hopefully see the presentation, and this time I need to share my system IDEO. Thank you. After the presentation, please ask any questions that you want from Naveen, and let me know if you cannot hear, you don't have the audio, and I'm gonna shut down myself.
I'm very interested in sports, and programming, especially in freelancing. Now here, artificial intelligence. What is artificial intelligence? Artificial intelligence is a broad area of computer science that makes machines feel like they have human intelligence. The goal of AI is to mimic the function intelligently and independently. Next, who is the father of this great AI? John McCarthy is the father of AI. McCarthy coined the term AI in 1955 in connection with a proposed summer workshop at Dartmouth College, which many of the world's leading careers in computing attended. As part of refining his idea about AI, he also invented programming language LISP, LISP in 1958. The three types of artificial intelligence. Now you will get confused. Why I divided it into three types? Genuine question. These are the classification by the capability. There are also classifications based on functionality, which is reactive machines, limited memory, theory of mind, self-awareness. Firstly, artificial narrow intelligence. Narrow AI is a type of AI which is able to perform a dedicated task with intelligence. The most common and currently available AI is narrow AI in the world of artificial intelligence. Narrow AI cannot perform beyond its field or limitation, as it only trained for one specific task. Hence, it is also termed as big AI. Apple series are a good example of this AI. Secondly, that is AGI, Artificial General Intelligence. General AI is a type of intelligence which could perform any intellectual task with efficiency like a human. The idea behind the general AI to make such a system which could be smarter and think like a human by its own. The worldwide researchers are now focused on developing machines with general AI, as systems with general AI are still under research and it will take lots of effort and time to develop such systems. Finally, the super artificial super intelligence. Super AI is a level of intelligence of systems at which machines could surpass human eye or human intelligence, which can perform any task better than humans with cognitive function. Some key characters of strong AI are capabilities include the ability to think, to reason, solve the puzzle, make judgments, plan, learn, and communicate by its own. Super AI is still a hypothetical concept of AI. Development of such systems in real world is still world-changing task. This is a crucial part of AI when it goes for AI discussion. How can AI be dangerous? There will be autonomous weapons, also social manipulation. Third one is invasion of privacy and social grading. And the last one, this is the biggest fear of AI researchers, misalignment between our goals and missions, or unclear vision of missions action to goal. After all, there are lots of AI merits and demerits, but this is the solution I found out. The good can outweigh the bad if managed properly. Like bad can become good if it's under the control of the teacher. I hope you all understand AI. It is a very big topic, but I try to summarize it. I take some points and presented here. Anyway, have a good day. Anyway, have a good day. Thank you.
Naveen, great. Thank you so much. I think it was a nice short presentation, bird view on AI and some future concerns about it, security problems that can create people sometimes are worried about. And it's a very controversial topic. Thank you so much. From students, other people, if you have any questions, please go ahead. You can ask Naveen about it. Um, if there is any question, please ask Naveen. Okay, if there is no question, uh, I would like to thank everybody for being present today here, and please don't forget to make your presentations. This is a time to practice telling others about your interests and telling others what you like and what you think you will be doing in the future. I guess for Naveen, we know now he's interested in AI and he has started uh, reading about it. Thank you so much. If there's any question, please ask. Otherwise, have a great weekend, and we'll see you next week.